Hello friends, welcome to CEC live lectures. Dear friends, in this session once again we are going to talk on data representation. We have conducted one session on data representation. This is the second one where once again we are going to get in-depth knowledge on the topic, and we would be continuing further from the point where we left in the previous session. Friends, for the discussion on the topic, we have with us in our studios Dr. Pavitra Bharadwaj. Dr. Pavitra Bharadwaj is Assistant Professor in Department of Computer Science, Jesus and Mary College, University of Delhi. Friends, if you wish to ask questions from Dr. Pavitra Bharadwaj, then you can contact us through our toll-free number. Our number is 1800110430. I repeat, our number is 1800110430. All dear friends who are watching us right now are requested to call in the last 10 minutes of the lecture only, and your questions to be relevant and associated with the subject only. Now I would like to welcome our guest, Dr. Pavitra Bharadwaj, once again. Hello ma'am, welcome to the lecture.
Thank you. Good afternoon. In continuation with our lecture on data representation, today also we are going to talk about the different conversions, and then we will be talking about how we can perform addition and subtraction on binary numbers. So just a quick recap of what we were discussing last time. We were talking about how data is represented in computers, and we said that data could be in any form like audio, video, text, visuals, images, graphics. Any kind of data is there in the computer. It is represented in the form through multiple bits, and each bit represents a particular code, and the value of that code will represent a specific character. So whatever values are being represented, whether they are characters or numbers, images, etc., ultimately what is stored in computer is a string of zeros and ones, that is a binary number. 0 and 1 we had discussed that all computer data is stored in the form of zeros and ones only. So therefore it becomes important to understand that what are binary numbers, what is this format in which the computer stores the data in itself, and also to understand the different ways, other ways in which numbers are represented. So these two lectures basically are concerned about how different formats can be used to represent numbers with different bases. So in the previous lecture we had discussed that basically we have two types of number systems, or two types of ways in which numbers are represented. Like we said that there is a positional number systems, and then there are non-positional number systems. So non-positional number systems are like the Roman number system which we follow, where the position of the number or the position of the symbol is not important. So wherever you place the digit or wherever you place the symbol, its value will remain the same. Even if you change its place, the value will not change. Whereas we have another kind of system which is known as the positional number system, where we have each digit or each symbol of the number system, the value of each symbol depends on its position in the number. For example, in the number 189, 9 is the value of the digit 9 is 9, but if I say 198, then the value of the digit 9 then becomes actually 90, and if I say 918, so then the value of the digit 9 becomes 900. So actually the position of the digit in the number determines the value of that digit. So basically we had discussed that in positional number systems we were talking about four types of number systems, and we had talked about the binary, the decimal, which is the usual number system that is the most commonly used. We had talked about the octal number system. Octal number system means where the base is 7, that is the base is 8, where the total number of digits in the number system is called as the base, and base is 8 means that there are only 7 symbols in the octal number system, 8 symbols in the octal number system, the digits 0 to 7. And in hexadecimal number system we have 16 symbols or 16 digits, 16 individual characters. So you have 0 to 9 and then A to F. So this way you represent the 16 different values, 16 different symbols using A 0 to 9 and then A to F. we had also discussed how we can change the numbers from the base 10 to each of these, that is to the base binary, to octal and to hexadecimal, and we had also seen how we can change from other bases to base 10, that is back to the decimal number system. Today in today's lecture we will see how you can convert numbers from binary to octal and from octal back to binary. Same way how we will convert the numbers from octal to hexadecimal to binary and back to binary from hexadecimal. So, we will begin with binary to octal conversion. So, we know that the maximum number or the maximum value which is represented in 3 bits can be 2 to the power 3 minus 1, that is equal to 7. Therefore, by using 3 bits we can represent the value 0 to 7. Therefore, 3 bits are sufficient to code any value in the octal number system. So, wherever you have 0 to 7, so these are the digits of the octal numbering system. So, 3 binary digits can be converted into 1 octal digit. So, we will use the combination of 3 binary digits to show or to represent 1 octal. So, the basic conversion or the basic representation will remain the same as we had seen, and we are only just going to do a conversion by grouping the number in groups of 3 here in case of binary to octal conversion. So, you can see here in this table you have 3 bit groups, that is 0 0 0 shows the decimal digit 0 and also the octal digit. Then you have 0 0 1 which represents the decimal digit 1 and octal digit 1, and then you have 0 1 0 which is actually equivalent to the decimal digit 2 and also octal digit 2. Similarly, you can see, so you have the binary number 1 1 1 which is equivalent to the decimal digit 7, and in octal also it is considered or it is represented by the digit 7 only. So, these are the 7 digits in the octal number system 0 to 7, and for each of these there is a binary equivalent that we can see. The binary equivalent is actually the procedure for obtaining this binary equivalent is the same like we had done for the division remainder technique that we had seen in the previous. So, by that you can easily find out the binary equivalent of all the numbers from 0 to 7. So, we see a simple conversion of octal to binary. See how it is done. So, if we have a number 742 with base 8, that is it is an octal number, and we have to convert it to a binary number. So, each digit is converted into 3 bits of binary number. So, we convert 7 is represented by 111 in binary, then we convert the digit 4. So, 4 is represented by binary 100, then we see the digit 2. So, 2 is represented by the binary digits 010. So, if you want to find out the complete octal number in binary, you only have to club all these and write. So, you can see here how we write this. So, the binary number that you see is a combination of these 3 bits. So, here you can see that a 9 digit binary number can be represented as a 3 digit octal number. Therefore, these are different ways of representing numbers, and one could be more precise than the other. One could be a shorter method of representing than the other, but then in computer science different fields and different number systems, they find different kinds of applications also. So, this is a simple example that we have seen of how octal to binary conversion can be done. Now, if we see conversion of binary to octal, again the procedure is the same, that is you have to make groups of 3 bits, and for each group you find the octal equivalent. So, if you want to convert a binary number which is shown here in the example like 101001110, this is a number with base 2. So, this means it is a binary number, and you want to convert it to octal number. In that case, what you do is that you start at the rightmost end and you split it into the groups of 3. So, starting from the rightmost end, you start grouping the binary digits into groups of 3, and in the last you can insert 0. If a digit is less, you find only 2 digits, so then a preceding 0 can be inserted. So, you can see here that we have divided this binary number into groups of 3 starting from the right end. This is very important to note, that this grouping will always be done from the rightmost end. So, because the leftmost digit you can see here is 10, so a preceding 0 can be inserted for understanding and clarity. So, 110 is equivalent to octal number 6, 100 is equivalent to octal number 4, and 10 is equivalent to octal number 2. In this case also the same thing, that the empty digits can be padded with 0 for more clarity. So, the binary digit that we see here is actually an octal number 246. So, you just write the numbers in the order in which they are done. So, the conversion procedure is quite simple, as you can see, that we begin from the rightmost end and you group the digits into groups of 3. If there is any empty digit left, then you pad it with a 0, and then you convert each of those groups, you find the binary or you find the octal equivalent, and then you club them and convert them as one number. Now, next is how to convert a binary number to a hexadecimal conversion. Hexadecimal, as we all know, hexadecimal means that the number system has 16 symbols. 16 symbols means that you have 0 to 9, then A is representing 10, B is representing 11, and so on and so forth, and then finally F represents the number 15. So, when you want to convert a binary number to a hexadecimal number, the procedure you follow is similar to what we have done in binary to octal conversion, but the important thing to note here is that now you will need 4 bits, because 2 to the power 4 is 16 and minus 1, so you have 15. So, total 15 symbols can be shown other than 0. So, you can see here that the maximum value represented in 4 bits is 15. So, we use 4 bits to store the values or to show the values from 0 to 15, and these are the digits of the hexadecimal number system. So, you have 0 to 15, and we have seen that 10 can be represented by A and so forth. So, the 4 binary digits can be converted to show one hexadecimal number. So, 4 digits are required to show one hexadecimal number, at most 4 digits are required. So, you can see here in this table that we form groups of 4 bits, and you can code in the third column. You can see we have hexadecimal digits. So, you have 0 to 9, and then A is coded as 10. So, 1010 will represent the decimal digit 10 and the hexadecimal digit A, and 1111 will represent the decimal digit 15 and the hexadecimal digit of F. So, this is a simple chart which shows the conversion for each hexadecimal number and its binary equivalent. So, you can see here, when you do the binary to hexadecimal conversion, you want to convert this number 1101001110. This is a number with base 2, that is, it is a binary number. You want to convert it into hexadecimal number. So, again the procedure will be the same, that is, starting from the rightmost end, you will start forming groups of 4, and because this is hexadecimal, so you form groups of 4, and for each of that group you will find out the corresponding hexadecimal digit. So, you can see here we have 2 groups in this, one is 0110, the other is 1010, and then the last digit 1 is left. So, as we did in the previous example, we can pad this with empty spaces with 0. So, your last group will actually become 000, and you can add, then you can put the 1. So, now you find the equivalent. So, 0110 means 6, 1010 means 10 in decimal and A in hexadecimal, and then you have the only digit 1, which means 1, and you can pad this with 3 preceding zeros, anyways, which makes no difference, but that is more for clarity and understanding and for creating a uniformity in the procedure. So actually the number which is coded through this becomes 1A6. So this is the hexadecimal representation of the binary number. Now if you want to convert a hexadecimal number to binary number, again what you do is that for each hexadecimal digit you find out the 4-digit binary number, and then you combine all those 4-digit binary numbers, so that will give you the total binary equivalent of the hexadecimal digit. So if you see here in the example, we have a hexadecimal number 3D9. Now you want to convert it into binary. So for each of these digits we will find out the binary equivalent. So first we will find out the binary equivalent for the number 3. Now number 3 actually is 11, but because we want it to be in 4 digits, because it is a hexadecimal conversion, so we put 2 zeros. Then for D it is 1101. So this number 1101 stands for D, and then you have the number 9. So 1001 is the binary equivalent for the number 9. So the total number that will be the total number which is representing 3D9 with base 16, or the hexadecimal number 3D9, is actually can be removed like this, and you can remove the leading zeros, because leading zeros makes no difference. So you can easily remove the leading zeros. So then the number can be obtained. So similarly we have, this is the conversion from any base, either octal or hexadecimal, to the base 2. In the previous lecture we had seen how you can convert from any base to base 10, that is to decimal and back to the original base from decimal numbers. Now we will see a different kind of conversion, that is conversion between octal to hexadecimal. That is for this octal to hexadecimal, actually what you need to do is, or hexadecimal to octal, the best way to do is that you convert the octal number into the binary equivalent, and then from the binary number you obtain the hexadecimal number. The similar reverse process can be used for conversion from hexadecimal to octal numbers. So to convert between octal and hexadecimal numbering system, the first thing is that you convert to base 2, and then you convert the binary number which is obtained to the new numbering system. So then intermediate, the best way is to put the binary number system as an intermediate number system. So in this you can see same way from octal to hexadecimal also the same method is used, that is you convert from one system to binary and then from binary to the new numbering system. So for example, if you have to convert this number E8A, which is a hexadecimal number of course, into the octal, so then first thing that you do is that you convert each of these digits of hexadecimal into binary. So the binary equivalent of each of these digits can be taken out for E, for 8 and for A, and then for each of these you regroup them into groups of 3 bits, because for octal you need 3 bits. So you regroup them into bits of 3, starting from the right side, and then after that you convert the binary number into octal number. So this will give you the octal equivalent of a given hexadecimal number. The procedure is simple. Once again I can tell you that for each hexadecimal digit you find out the 4-bit equivalent binary number, 4-digit equivalent binary number. Then you make another grouping of 3 bits starting from the right, and those 3 bits can then be converted to get the octal equivalent. So you will get the octal equivalent of the given binary number. So octal to hexadecimal conversion, this is another example where we see you have an octal digit 752 and this needs to be converted into hexadecimal. Again the procedure is going to be the same. For each octal digit you find out the equivalent binary number, then you rearrange into groups of 4 because now you want to convert to hexadecimal. So, the rearrangement will be in groups of 4, and then of course, you can pad them with the empty spaces with zeros. So, you regroup by 4 bits, and then for each of the 4 bit group you find out the hexadecimal equivalent of that given binary number. So, you get the hexadecimal equivalent of the given octal number. So, we have seen how you can convert the number systems from octal to hexadecimal and hexadecimal to octal number system. So, we have seen in this part of the lecture that what are different types of number systems and how we can convert from one base to another. Similarly, you can have any base number converted to any other base number by converting it into a binary equivalent. So, you can get a number in any number system and you can convert it into binary before you convert it into any other type of number system. So, this is about conversion. Now, the next important part of the computer binary number systems is how you can calculate or how you can perform arithmetic on the binary numbers. So, binary arithmetic is very much similar to the decimal arithmetic. The same concept of carry and borrow is applied in case of addition and subtraction as we use for decimal number systems, but there is a slight difference because here we only have 2 bits, that is 2 digits 0 and 1. So, the general rule remains the same, but their representation is slightly different. So, in this part of the lecture now we are going to talk about how you can add or how you can subtract 2 binary numbers. But before actually we do the binary addition, we will just have a basic understanding of or a basic run through of how the decimal arithmetic is done or how addition of 2 decimal numbers is done, and the concept of carry, that is how this carryover thing works when we are adding 2 decimal numbers. So, you can see here I have 2 very simple numbers and I am going to perform the addition. So, we add 8 and 17, so 8 and 7, so the answer is 15. So, you write down 5 and you carry 1. This is simple. Then again you add 5, 5 and 1. So, you get the answer as 11. So, you put 1 and you take 1 as the carry. Now, you add 7, 6 and 1. Again you put 4 as the number and 1 you carry. And in the next step you have 3, 4 and 1. So, you can simply write down the answer 8. Now, if you see here, if we try to look at it at a different way, so we see in this case that when we have this number, when we add 2 numbers which have a carry, so basically from the sum we are subtracting the base is 10. So, we are subtracting the base and whatever is the answer we are writing that and we are carrying over 1. So, basically when you have a addition where you have a carryover, so you subtract the base of the number. So, the base could be 10, it could be 2, it could be 8, it could be 16. So, in all types of additions, this general rule is followed for carryover for addition. So, when the sum of a column is equal to or greater than the base, we subtract the base from the sum and record the difference and carry 1 to the next column to the left. So, when their difference is more than the base, then what you do, or when the sum is more than the base, then you subtract the base from the sum and the number which you get, the difference what you get is the number and the digit 1 will be carried. This is for base 10. Same rules will apply for numbers with other bases also. So, now if we come to binary addition rules, so binary addition is again very simple because you have only 2 bits here. So, we say when you add 0 and 0 you get a 0, when you add 0 and 1 you get a 1, when you add 1 and 0 you get a 1 again. So, this is same just like decimal. Now, the difference is when you add 1 and 1. So in binary representation you show 2, in decimal representation you show 2 as the digit, but the digit 2 is represented as 10 in binary. Now when we say it is 10 in binary, so this means you will write down the answer or write down the number 0 as the answer, and 1 you will carry over to the next thing. So this 1 will be carried over. If you have 1 plus 1 plus 1, that is you have 3. So it is represented by the digit 3 in decimal, and in binary you represent it with 1 1. So you add 1, you write as the number, and the other 1 you take over to carry. So basically the rule remains the same, that is when the sum of the two numbers is more than the base, that is more than 2, in that case you subtract the difference and you subtract the number, the base from the number, and the difference you write as the number and you carry over 1. So if we see here, this is a very simple example of adding two binary numbers. So you add two binary numbers and you have 110 111, and the other number is 011100. Now in this case, when you are trying to add these numbers, it is quite simple. You add 1 and 0, so the answer will be 1. Again the next is 1 and 0, so the answer is 1 again, so you write 1 here, again 1 and 0, so you write 1 here. Now in the third you have 1 and 1, so when you add 1 and 1, so actually the answer is 2, which is represented as 10 in binary. So you write down the 0 and you carry over the 1. Now in the next step again you have 10 which becomes 1, and then 1 plus 1, so this is again equivalent to 2. So 2 means you have 10, so you write the number 0 and you carry over 1. Again 1 is carried over. Now you have 1 plus 1 plus 1. So this is equivalent to the decimal number 3, which is represented as the binary 1 1. So this will again come 1 and 1 will be carried over. Now you have 1 1 again, so the answer is 10, so you write 0 as the number and again you carry over 1. Now this 1 can be simply carried down and you can write 1 here. So this is the answer, this is how it is carried on. So now basically we have seen how simple binary arithmetic can be done. We will be looking at a few more examples of it in a short while. Till then, thank you.
With this note, thank you ma'am, thank you so very much for giving us this session. Friends, you are requested to be with us as we are back after a short break. Thank you. Hello friends, welcome back to this session. Friends, as you know that today we are elaboratively talking on data representation. Through the previous session you have gathered maximum of knowledge, and as promised here we are again for you to give you the maximum knowledge once again. Friends, for the discussion on the topic we have with us in our studios Dr. Pavitra Bharadwaj. Dr. Pavitra Bharadwaj is Assistant Professor in Department of Computer Science, Jesus and Mary College, University of Delhi. If you have any set of questions, then you can ask us the questions live live through our toll-free number. Our number is 1-800-110-430. I repeat, our number is 1-800-110-430. You are just requested to call in the last 10 minutes. Now, I would like to welcome our guest, Dr. Pavitra Bharadwaj, once again. Hello, ma'am. Welcome to the lecture.
So, we were talking about how two binary numbers can be added, and we had seen that the basic rule remains the same, and we had discussed an example also. Now, we are going to see how this works, or what is the explanation behind this calculation. So, we can see here that you are adding these two binary numbers which are given as 110111 and 11100. Now, if in the first two column there are no carries, so it is simple. You can just simply 1 plus 0 is 1 and again 1 plus 0 is 1. Now, in the third column you have 1 plus 1 which is equivalent to a binary to the decimal number digit 2. Now, since 2 is equal to the base, so subtract the base from the sum and carry 1. This is the rule which we have seen in the decimal arithmetic also, that is, you subtract the number from the base, that is from 10, and you write it. So, here again you are doing the same thing. So, since the base is 2 and the answer is also 2, so you write 2 minus 2 is 0. So, you write 0 and you carry over 1. So, this is how it works. Then again you have 1 0 is 1 and 1 plus 1 again is 2. So, in column 4 also we subtract the base from the sum and carry 1. So, this again becomes 0 and you carry 1. Now, in this next column we subtract the base from the sum and carry 1. So, the base here, now the number becomes 3 and you subtract the base is 2. So, your answer gets, the answer you get is 1 and the carryover is again 1. So, you have again 1 plus 1, the answer is 2. So, 2 minus 2 becomes 0 and you carry over 1. Now, in the 7th column there is nothing, so simple 1 is copied down, so it is brought down from there. So, this is how this simple binary arithmetic or binary addition can be done. The rule remains the same as we have seen for the decimal numbers, and the carryover rule also remains just the same, with the only difference that in decimal, of course, the base is 10. So, you subtract the number from 10. Here the base is 2. So, you subtract the number from 2. And it is always advisable that whenever you do a binary addition, then you calculate or you perform a verification to check that the answer that you are getting is correct or not by converting the numbers into decimal numbers. So, you should always do that, because that will ensure that the procedure and the answer you have obtained is correct. So, here we can see how the verification can be done. So, you convert the numbers into decimal numbers, each of the binary number is converted into decimal number and they can be simply added. So, you get the answer. So, you can verify the answer. Now, this is another example of how binary addition can be done to explain or to see the concept of addition with more greater clarity. So, this is these are two binary numbers that we want to add, 111010, 001111. Now, you want to add these two numbers. So, the first column is a simple column because you only have to write 1, 0 and 1 becomes 1. Now, in the second column it is 1 and 1. So, we just seen 1 and 1 means 2 and 2 can be represented as 1 0. So, 0 can be written here and 1 is carried over. Again in this column it becomes 1 1. So, 1 1 is again you write the number 0 and 1 can be carried over. Now, this number becomes 1 1 1, that is equivalent to 3. So, 3 is represented in binary as 1 1. So, again you will write the number 1 and you will carry over 1. Now, you have again 1 1. So, this 1 plus 1 in binary becomes 2, which can be represented as 1 0. So, you write 0 here and 1 you carry over, and then you again write 1 plus 1, which is again 2. So, you write 1 0. So, 0 is written here and 1 can be simply written down here. So, this way you can see how the calculation is performed, and a verification or a back calculation to convert it into decimal and C is also can be done to ensure that the calculation is absolutely correct. So, this is how addition is done. The next thing that we do is how to subtract the numbers. Now, simple subtraction is easy to understand. Here we are also going to talk about the concept of borrowing. So, we can see here, which is we begin with the decimal example only. So, the number is 8025 minus 4657. So, you can see these are decimal numbers. So, we subtract 5 from 7, you can't. So, we must borrow 10 from the previous column. So, when you borrow 10 from the previous column, so this number becomes 15. So, now you can do 15 minus 7. So, you get the answer as 8. Now, again in the previous column, now it becomes 1 minus 7 cannot be done. So, again you borrow 10 and similarly you get the answer, that is 11 minus 5. So, you get the answer. So, you add the borrowed 10 to the original 0. Now, you can borrow 10 from this column. So, now when you borrow 10 from this column, so this becomes 9. So, similarly you can do the calculation for this also. 9 minus 6 is 3 and 7 minus 4 is again 3. So, you get the number 3368. This is a simple example of how decimal subtraction can be done. Now, if we look at the explanation or the theory behind this subtraction, so it is simple that when you cannot subtract, you borrow from the column to the left, and the amount which is borrowed is 1 base unit. So, in decimal that base unit is 10. So, whatever you borrow, you will borrow in that base unit, that is you always borrow a digit 10, and in case of binary also we will do the same thing, but in binary what you will borrow is again the base unit. So, your base unit there will be 2. So, you will always borrow in the base unit 2. So, similarly you add 10 to the original column value, and then we always understand. So, this will be a simple subtraction. Now, if we look at a binary subtraction, in binary the base unit as we just discussed is 2. So, when you cannot subtract, you borrow from the column to the left, and the amount that you borrow will always be 2. So, 2 is added to the original column value. So, you will be able to subtract. So, when you add the 2, you will be able to subtract. So, if we see here, these are the numbers that you want to subtract. So, you have 1 1 0 0 1 1, and the number to be subtracted is 1 1 1 0 0. So, in the first step it is simple, 1 minus 0 is 1. So, you write 1. Again in the second column also 1 minus 0 is 1. So, you write 1. Now, in the third column you have 0 minus 1, which cannot be done. So, you must borrow 2 from the column on the left. So, the next column on the left is also 2. So, you must again go to the other next column wherever you find a 1. So, you borrow from this column. So, this becomes 0 and the column to the right becomes 1 0. Now, when 1 is added, so this becomes 2. Now, from this 2 you borrow 1 and it becomes 1 again, and the other column becomes 1 0. So, this is 2 minus 1. Now, the other column which you have is 1 minus 1, which is 0, and you subtract 1 minus 1. So, you write 0. Then you have 0 minus 1, which cannot be done. So, again you do the same thing, that is you borrow from the column on the left. So, this borrowing will become a 0 here, and this will become a 1 0, that is 2. Again you will say 2 minus 1 is 1. So, you can write 1 here. So, you get the number 1 0 1 1 1. Remaining leading zeros can simply be ignored. So, this is how a simple binary subtraction can be performed by using the same technique of borrowing as we have done in this. Now it is also important, like in addition, it is equally important to verify the answer that you get using the binary subtraction also, because verification of answer is a very important element in this case. So when you will verify the answer, you can see by converting the numbers into corresponding decimal numbers and doing the subtraction. So you will see that the answer that comes is correct. Now we will do one more example to understand how binary subtraction is working. So it is again 10100 is subtracted from 101001. So you can see here 1 minus 0 is 1, 0 minus 0 is 1. Again now you can see it is a 0 here. So what you borrow is 1, that is you borrow a base unit 2. So this becomes 2. Now this number 2 minus 1 is 1 and 0 minus 0 is 0. Again what you see is 0 minus 1, which cannot be done. So you again borrow. So what you borrow is a base unit, that is 2. So then it becomes 2 minus 1. So it gives you the answer 1. So and the verification also shows that the procedure that is being used is correct. So we can see now how binary addition and binary subtraction has been performed. The basic rules of addition and subtraction are the same that we are using, but there is a slight difference, that is in decimal we have been using a base value of 10. So all the borrowing and all the carrying over was done with the base value 10, and here we were using the base value of 2. So whatever borrowing is done with the base value of 2. This is the only difference that we must understand. Another point which is important to remember while performing any kind of binary arithmetic, that a verification is a necessary condition. Unless you verify by converting the the binary numbers into their decimal equivalent, you cannot be assured that the answers are correct. So verification is one of the most important steps after conversion and after addition subtraction of binary numbers has been done to ensure the correctness of your solution. So this was about binary arithmetic. Now we will talk about some logical functions that a computer undertakes, logical shift and rotate operations. So in this we have logical bit twiddling and logical shift operation. So we have logical OR rules and we have so we will talk about the OR operations. OR results in 1 if either both of the operands are 1. So this is a logical operator which shows that both the results are, when both operands are 1 or either of operands is 1, then the result will be 1. For example, if you have 0 and 0, then the answer will be 0, 0 or 1. So since there is single 1, so the answer will be 1. If you have 1 or 0, then the answer is again 1, and if you have 1 and 1, since both are 1, then also the answer will be 1. So if we see the logical OR operations here, you can see that whenever we have, because these logical OR operations and all these logical operations and OR and NOT and XOR, these are all used in computer circuits. So these operations, they are used to find out the result of various operations that will be performed on data within the computer. So these are special circuits in the computer called gates, which performs calculation depending upon the value of the voltage. So this is a very important aspect and it is related to how computer architecture can be designed. So to perform the OR operation, we take one column at a time and perform the OR operation using the OR table. So you can see here, because we have seen if either of the digits is 1, then the result of the OR operation is going to be 1. So you have 1 1, since both are 1, so the result will be 1. In the third column you can see if you have a single 1 also, then also the result is going to be 1, whereas only when both the operands are 0, the result is going to be a 0. So, these are logical operations which are used for combining conditions. So, here 1 and 0 can also be understood in the form of true and false conditions. So, when you have true and false conditions, then also the same thing can be understood as combining of different logical structures together and getting a suitable answer for that. So, you can see here again, this is an example of how logical OR operations can be done. So, you have 1 0, again 1, only when both the operands are 0, the answer is coming to be 0. In all the other cases, the answer comes to be a 1. So, another example is also showing the same thing. So, you have when you are performing an OR operation, then you get the answer as 0 1 1 1. Then there is another very important logical operation, that is called XOR. Now, XOR, actually here X stands for exclusive. Exclusive means it is similar to OR, except that it gives 0 when both the operands are 1. So, basically OR will give a 0 only when both the operands are 0. Here it will give a 0 when both the operands are 1 also. That is, it will give you a 1 value when the two operands are different. In any case, if both the operands are same, the answer will be a 0 with an XOR type of operation. So, you can see that when we have a 0 and 0, then also the result will be 0. When you have a 0 and 1, then the result will be 1. When you have a 1 and 0, the result will be 1. But if you have both the operands as 1, that is 1 and 1, then also your result will be a 0. So, this is the difference between exclusive OR and OR, that in case of OR, when both the operands are 1, the result is 1. But in case of exclusive OR, when both the operands are 1, the result becomes 0. So, this is a major difference between XOR and OR. So, we can see here some of the examples are shown for XOR. So, you can see wherever you have both these operands are same, even when both operands are 1, the result is a 0. So, both the operands become 1 means the result for an XOR will be 1, whereas if it was an OR, then the result would have been 1. Then we have another important logical operation which can be considered similar to multiplication. So, it means that AND operation means that if both the operand 1 as well as operand 2 are 1, only then the result will be 1. That is, operand 1 has to be 1 and operand 2 has to be 1. If any of them is 0, then the result of the operation will be 0. So, you can see here 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and only when 1 and 1 are performed, the operation is performed, then the answer comes to 1. So, these are logical AND examples. So, you can see how the operations are performed. 1 and 1 will give 1, and other than that all conditions will give you an answer as 0. So, this is a logical AND solution that we see. So, this can be considered as similar to multiplication, because when you multiply 1 and 1, only then you get an answer as 1. If you multiply any number, any operand with 0, then the answer will be a 0 only. So, this can be considered as analogous to that situation. Then we have another operator, logical operator, which is called NOT. So, NOT is a separate operator for flipping the bits. Flipping the bits means that not true will be false and not false will be true. That is, not 0 will be 1 and not 1 will be 0. So, this is kind of reverse operation. This can be considered as a toggle operation between 0 and 1. So, you can see if we say not 1 0 1 0, in that case all the bits will be reverse. So, wherever you have a 0 you will get a 1, and wherever you have a 1 you will get a 0. So, if you apply this NOT condition, then it becomes 1 0 1 0. Now, we will talk about a very important part in computer arithmetic in case of binary arithmetic, that is how to find the complement of a number. So, basically the complement of a number, it stands, or it means that is the number minus the base raised to the power the number of digits in the number minus 1 minus the number itself. So, basically if you talk about binary numbers, the complement of the number can be obtained by reversing all the digits of the number. But here first we are going to see how you calculate the complement of a decimal number. So, this is the formula that we use for finding out the complement of a decimal number. So, here we can understand that B means the base. So, in case of decimal number system, the base is 10. N means how many digits are there in the number for which you want to find out the complement, and capital N stands for the number itself. So, basically you will subtract this value from the number to obtain the complement of the number. So, for instance, if you want to find out the complement of the number 37. So, now I am talking about decimal number 37. Now, we will use the same formula. So, the base here for decimal number is 10 and 37 has 2 digits. So, it becomes 10 raised to the power 2 minus 1. So, that becomes 100 minus 1. So, that is equivalent to 99, and then from this you subtract the number. So, this is 99 minus 37. So, the number that you get is 62. So, the complement of 37 is 62. Now, complements also have various applications in case of computer science and in case of mathematics. So, this is one method of finding out the complements of a decimal number. If you want to find out the complement of a binary number, the procedure is simple. You just replace all zeros with 1 and all ones with zeros. So, basically if you have a binary number like 1010101, so then you will get the complement of this number as 010010. That is, wherever you have a 0 you will put a 1, and wherever you have a 1 you will put a 0. So, this is going to give you the ones complement of the given binary number. So, basically when you are finding out the ones complement of the binary number, you just simply replace the zeros with the ones and the ones with the zeros. But if you want to find out the twos complement of the number, then you will find out the ones complement and you will add 1 to the number. So, when you add 1 to the ones complement, the result that you get is a twos complement. So, ones complement and twos complement of binary numbers is used very often when you are doing subtraction and complex arithmetic operations on these binary numbers. So, basically we have discussed that there is a lot of application of binary numbers in computer science, because we know that all data in computers is stored in binary format. Now, we also understand that computers are actually used for various purposes, and basically there are different codes which are used for coding or for following the for representing different characters in the computers. So, the first type of computer code that was used was the American Standard Code for Information Interchange, that is the ASCII code. Now, the ASCII code basically it had 127 different codes for the basic characters on the keyboard. So, 127 characters were used for coding all the characters like small letters, uppercase letters, lowercase letters, and some special characters which are there on the keyboard. So this was ASCII 7. Then we had ASCII 8, which had 256 characters or 255 characters basically, which were available. Codes for these characters were available. Their binary equivalent codes were available for coding the different characters. But then as the use of computers grew, a large number of symbols kept on being added. Nowadays computers are not just used for English speaking purposes, but a large number of languages and scripts of the world are being used through computers. They are being processed through computers. So for each one of these, the computer needs to have specific codes. So ASCII 7 and ASCII 8, gradually they fall short of codes for processing of these numbers. So a new system of coding of characters has come up, and this new system or this new theme of coding is known as the Unicode. So Unicode basically refers to a new kind of code which is given to different characters which are used. So Unicode not just has codes for English language or English characters, but it also has codes for all languages of the world, and you have up to 2 to the power 32 different symbols which are available in Unicode. So as of now, for all practical purposes, Unicode is serving as a good mechanism for coding the different symbols, mathematical, scientific symbols, and for all other languages. All languages of the world can now be represented in the computer because of this Unicode coding system. So basically Unicode also means that for each symbol of each language you have a corresponding binary code for that. So these binary codes are again used for all these symbols. So we see how important binary coding schemes are for processing different types of data that is present in the computer. So with this we come to the end of our session on binary numbers and binary arithmetic. Thank you.
With this note, thank you ma'am, thank you so very much for giving us this session on data representation. Friends, you are requested to write to us at info.cec@nic.in if you have any query or if you have any feedback which you likely to give to us regarding the lecture. We are going to meet again very soon. Keep watching us, keep writing us. We are going to meet soon. Hello. With this note, thank you so very much.